Cool.
Okay.
And the proposal was half an hour. Is that okay? At maximum, I think that for.
I will try. Yeah, I will.
Yeah. Okay.
Yeah, I will. So half an hour. Yeah. Okay. So
Cool.
the main idea is to try to derive some general ideas on what can be done and what cannot be done with integral field units or 3D spectroscopy based on models. So that we can explore the methods we are applying to the observations and see if they are biased or if there is some problem. So so this is a notebook. So it's running. I read it. So I read the model. So if at some moment you want to see something that I didn't plot other lines or something different, so you can ask me and I can do a new plot. Okay. So well, the idea is I run a grid of model. So here is okay. So the model, photoionization model, cloudy, I ran with the latest version that they published 2 days ago. So the ionizing source is a BPass, so binary, including a stellar evolution model of stellar atmosphere and all these kind of things. So it's quite a good description of spectral energy distribution. The abundance ratios are changing following a paper by Nichols a few years ago, and the metals are depleted. Log U, so the ionization parameter, is decreasing with increasing oxygen. It's something that people observe. So, well, I'm using. We can change this. This implies running new models, so that will take times a little bit, a few minutes, but okay. The density is 10. Okay, it's not changing that much. The results, filling factor 1 also okay. And there is some dust in the model following O over H. Okay, and I chose nebula H region that are optically thick, but geometrically thick also. I mean, the inner radius is rather smaller than the expected Strömungen radius. So there is a structure that can be seen in the nebula. It's not a plane parallel, very thin shell. So, well, here are some formula that can be used. Okay, yeah. Okay, so we run the model. It's commented here. It's already run. It's stored somewhere. Okay, and I read all the models. So I made basically running a model between O over H between -5 and -3, 17 models, 2 million years. The ionizing cluster is 2 million years old. Okay, and FR is this form factor. Okay, shape factor. Okay, and there is some dust. Okay, yeah. So it has been run. And what I do is I read the cloudy model, which are 1D model, and I made a 2D model. I could have made a 3D model, but it's spherical model. So I just need 2D and to project and to see what's happening. Okay, so just to have a look at, to be sure that everything went fine. So log U is clearly decreasing with over H. It's one of the hypotheses, so it's okay. N over A is increasing with over H. Okay, that's fine. And this is a BPT, classical BPT diagram with the 3 classical demarcation lines or border lines, Kuhli, Kaufman, and Stasinska. Okay, and we see that each dot here is one of the 17 models I run. Okay, and the color code is the metallicity. Okay, it's not exactly where the H2 regions are found, but it's not that important in what I am doing here. I am not trying to make a fine-tune series of models, but I want to see the effect of models that are not trivially stupid. I think it's the case. Okay, so these are the maps of 3 of the 17 models, the ones that are in the center part, not the extremely metal poor, not the extremely metal rich, but the central guys. So the number 7, 10, and 13 in the grid of models. So that's more or less what we are dealing with, you know, with close H2 region. Okay, so here are the cut in the model. So it's not a projection still, no? It's just a cut. So you can see that when the abundance is increasing, the ionization factor is decreasing. So the low ionization spaces are more important. Here, so for example, you see that N2 is more important in the in the right column, where they are a little bit metal-rich guys. Okay, and the contrary for O++, obviously, O3. So O3 is more important in the left column, where the metallicity is lower, and so the ionization fraction is higher. Okay, so yeah, all those guys. Yeah, so this is 100 by 100. It can be more, but it's enough to have a kind of good resolution to play with. So first of all, I will check that the integrated guys, the parameters are what we expect. So here are the integrated nebula. So one value for each nebula. This is the temperature of O++ from the model in orange, and from PINEB based on auroral to nebula line ratio, the classical direct method to determine temperature. Okay, and we see that both are quite good. I may have different atomic data and cloudy. I should fine-tune this, but that's very close together. So determining the temperature from PINEB using the line ratio is a good idea. It's not that bad for integrated objects. Okay, and the same for the ionic spaces. So O++ here is increasing with the metallicity, the contribution of O++. Okay, because O over H is increasing, and also because its contribution is more important because the ionization parameter is decreasing. And the sum of both of them, O++ plus O++, O++, determined from PINEB, this is a solid green line, is very close to the black line, which is the actual input in the model. So we are recovering the O over H, so everything is fine, great. Now let's do the same, but for spaxels. So I put my map, my cut in the nebula, I make horizontally, and I integrated over the radius, okay? So I chose one of the 17 model, the guy in the middle, more or less, with over H of 8.25. So the model number 11. You can change this, and I will provide you everything to play with this. So this is a kind of regular abundance, okay. This is the temperature I determine from the integrated profile. So now it's not the whole guys, just spaxel by spaxel. So on the x-axis, I am plotting the results of the spaxels from the central part of the nebula until the end of the nebula, okay? So it's like an observation through a long slit, let's say, or sorry? Okay. It would be the same for resolved nebula with axisymmetry. Okay. So the black dot is the actual temperature within the nebula. We don't have access to this because all we have is integrated temperature. So, and it's starting, there is an empty cavity in the model. So all this inner part, there is no gas. And so this is an actual temperature structure of the nebula. But what we are detecting is not the structure of the nebula, but the structure of the projected nebula. At the point, okay, but that's quite fine. We can see that we recover the temperature quite well with O++ and N+ with PINEB. Okay. The same with the unique abundances. So the stars here are the O+ over H. So in the central part, it's quite low, and then it's increasing outward. And the dots are the O++ here, okay? And the sum is the diamonds here. So we are recovering the O plus plus O plus plus over H beta or H plus using PyNeb, and the black dashed line is actual value of O over H. So that's quite fine. We can recover using the direct method, determining the temperature. Okay, I didn't take into account the density here. It's a simple model just to illustrate the things. Okay, so I can determine local or spatially resolved, let's say not local, but spatially resolved, projected on the sky plane. I can determine temperature, density, ionic abundances, and elemental abundances. That's quite fine, okay? Great. Now, let's see what's happening with the ICF. So the ICF are those parameters or factors that correct for the unseen ions. For example, N++ is not seen. It doesn't emit in the optical. There is no N3 lines. There is O2, O3, N2, but not N3. So the ICF is how you will determine the nitrogen abundances, even not seeing the N++ ionic abundances. So that's the point of the ICF, ionization correction factor. So you can determine this normalized by oxygen. You say, okay, I know N plus over O plus is close to 1. Okay, yeah, it's close to N over O, I mean. So the ICF is close to 1. And that's quite good. The ICF of the model, the global ICF is 1.1. And the ICF you determine using the projected observations is quite good. It's quite close to the value from the integrated object. Okay, so you can determine the same thing for chlorine. Chlorine is more complex. It's based on O++. The relation to determine the ICF has been published a few years ago by Amayo, Stadzinska, and collaborators, and Delgado Inglada. And this is a fifth order polynomial. So this is the value. So you can, and this is based on O plus over O plus over O plus plus. So the ionization of oxygen is a base to determine the ICF. And so you can see that it's not that bad, okay? The value, the real value is in blue, and the value determined from the relation is in orange. So that's quite good, and it takes into account the fact that it is decreasing. It is decreasing here, okay? So if you use this to obtain the chlorine over oxygen over the whole nebula, you can see that, okay, there is a shift that's not that big, okay, compared to the input value of the model, but it's quite horizontal. That's a good news. The point here is that the main idea behind the ICF is that you will look in a grid of models. ICF are based on models. You will look for regions in models, in a grid of models, where the ionization is close to your object. And you will say, okay, my ionization is determined by O++ over O++ plus O++, for example. So I am looking for models that have the same ionization for oxygen, and I will claim that chlorine is also well described by the model that describe my oxygen ionic fractions. So that can, this argument can also be built on spaxel based. In one given spaxel, I have an ionization. I'm looking for similar ionization in my models, and I will apply the look for the ICF in this model. So the ICF in first order is not that. It's not that bad idea to try to apply ICF computed for integrated models to resolve region, to spaxels, because the idea is looking for similarities in ionization. So the ionization is decreasing in outward in my model, but the ICF is taking this into account because it's based on the ionization. So that's good. And you say, okay, there is a shift here, but there is no wrong abundance gradients that appear due to the ICF. So chlorine over oxygen, which is constant in my model, this is one single model here, okay? It's not by grid of model, it's one of the models. The abundance is constant. And my determination of abundance is even with a strongly decreasing ICF and a strongly decreasing O++ over O is correcting on it's rather flat, I say. So there is no apparent gradient that is showing up that would be wrong. So it's not that bad. Okay, the outer part is totally wrong, but there is no O++ at all. So and when you cannot compute the ICF, the W that enter the formula here would be very badly constrained in the outer part of the nebula because there is no O++. Okay, that's fine. Now let's go to the point that made the title of this plot, what not to do with IFU. No? Okay, so the point here, let's plot the models in the BPT diagram. You know that BPT diagram is widely used for a lot of things, sometimes good, sometimes not that good. Okay, so what is giving you the BPT? The main idea of the BPT diagram is to give an idea of who is acting, who is ionizing and heating the gas. And these three separation here, borderlines from Kulik, Kaufman, and Statistical are telling the same stories. In the upper or right part of the plot, we can find hot nebula. I mean hot in the sense that what is plotted here is a ratio between the mainly collision excited lines over a mainly recombination lines in both cases. The dependence of this ratio on temperature is strongly increasing with temperature because of the both effect. No, forbidden lines, collision excited lines increase with temperature, and recombination line decrease with temperature. So the ratio is doubly increasing. So if you are in the upper right part of the diagram, you are dealing with hotter gas globally. Okay, whatever the ionization is. So, and OB stars can only put your nebula at some temperature that is, okay, given, depending on the analysis, but it cannot be twice the value that you expect. So in this upper part, you will see objects that are hotter than classical H2 region. So DIG, for example, ionized by Holmes, a hot low mass evolved star, or white dwarfs that are heating more the gas, shocks that are heating more the gas, AGN that are heating more the gas. So all the guys here are hotter than the guys here. Okay. So what it tells you is if you are above those lines, it is barely H2 region. It doesn't mean that if you are below the lines, it is H2 region. Okay, there are cool planetary nebula, there are cool shocks, there are, okay, so. Okay, the point here is, can we use this diagram when we have spaxels? Okay, so here each star is an integrated model, and each trace here is the spaxels correspond to the spaxel of the given region with the same color. Okay, so this H2 region is actually from the so the size is giving you the distance from the center. Okay, this is the central spaxel where you also observe the star, ionizing star or stellar cluster, and this is the outer part of the nebula. That's quite logical. You are going from a high O++ region, O n plus, to a low O++ and high n+. So you are going through the nebula, but it's projected. So it's not a cut in the nebula. What you observe is always a projection of a sphere. Okay. So very interestingly, the shape, the envelope of the spaxels is giving you the upper limit at least is almost the same as the integrated locus or loci of the models. So I was expected, but I didn't do the model till last week. I was expecting that it was perhaps going above, but it's not the case. But it goes below. So when you observe H2 region in this part, it may be that you are observing the outer part of the regions, Spaxel bars. Okay. And something quite interesting here is that you have a sequence in abundances or metallicity, as you want, okay? Going from upper left poor region to rich region in the lower right part of the BPT. So the BPT itself, it's something that tells you about the metallicity. It has not been used as this, but some lines, N2, for example, or O3 or O2, are used to make this strong line method and determine abundances. But it's all based on the same thing. Okay, so the same for S2. You can see that S2 is going a little bit at higher value. So external part of H2 region have high S2. It's not proof of shocks. There is no shocks at all here. It's pure photonization models. It's just you are entering the very low ionization border of the region. So S2 is intense and O3 is reduced. So you are in this part. So it doesn't mean if you go to higher value of S2 that you are entering into shock region. So just normal behavior. And the same for O1, so even worse. No? So the stars are the integrated guys, but if you are observing spaxel by spaxel, you can go to very higher value, quite rather higher values. It doesn't mean that there is something strange happening. It's just that you are observing the low ionization border of the nebula. It's normal. If you are astrophotographers or even you are looking at the HST or whatever nice observations, most of them are using a coding color with a red following N2 or S2 or O2 and the blue following O3. So the gradient in color is telling you exactly the same thing as this here trace. Now, blue, well, not blue here in the color, but in image, HST image. So the central part of the nebula is O++ dominated, and the outer part is low ionization guys. Great. So the same, but for another diagnostic that is used sometimes, S2 Verge alpha, N2 Verge alpha. So for a given metallicity, you can see that you can go very high at relatively higher 2 in S2 without entering a shock region. So take care of this. So people are using these strong lines when you don't have the direct method, which I showed you a few minutes ago that it's working fine. If you don't have the direct method, if you don't have temperature diagnostics, you can still claim you can determine abundances using this strong line guys. And so this is what I do here. So in X is one of the strong line calibrator or indicator, N2 over H alpha, the same as X in the BPT. Okay, so this is the same guys as here. Okay, here a strong line. Okay, but here in Y it's the metallicity. And in black, this is a Marino. Marino. Okay, relations. Okay, so it's not that bad. It's increasing. Okay, so ionization, metallicity is increasing with N2 over H alpha increasing. Okay, well, that's logical because I told you since the beginning that log U is decreasing with abundances. So if log U is decreasing, low ionization guys are increasing, okay? So N2 is increasing. But it's increasing because you take the whole nebula into account. So these are the stars here. But look at one, let's say, let's take the yellow guy. So this is one nebula, okay, with one metallicity, okay. So if you observe the inner part of the nebula, you will observe this N2 over H alpha ratio. If you use the Marino curve, you will go there, and you will say, okay, my metallicity, my over H, in the inner part of the nebula is 8.2, a little bit lower. And the outer part of the nebula is this one. Okay, you observe N2 is this. You go to this relation, so you will observe 8.4, 8.5. So 0.3 dex of apparent over H gradient. It has nothing to do with abundances. This guy here is one model with one single abundances, homogeneous abundances. The apparent abundance gradient is just due to the fact that you are using here an integrated based calibrated abundance determination. And it cannot be used at all for individual spaxels. It doesn't work. It cannot work by construction. No? N2 over H alpha is working because the global ionization of the H2 region is changing with metallicity, but not the local. The local one is something local. That's the same issue here as mixing meteorology and climatology. Okay, climatology is telling you that there is a global warming, but it's not because today it's a little bit cold that climatology is wrong. It's just because today is a matter of meteorology, nothing to do with applying a global model. So that's the same here. Okay, this black line is obtained by a calibration of integrated objects that are including something that is related to the object at all, the global ionization of the object. Okay. The same with O3 over N2 in the opposite direction, but will give you the same apparent gradient. Okay, it's decreasing here, but from the center to the outer part, you go to the left. So that's the same idea. You will determine the same wrong abundance gradient from your spaxel observation, base observation. Oh, this one is wonderful. Yeah, good. We have a good one. N2 over O2. Okay, that could be a solution because there is it's low ionization, so there is no effect of ionization in this. The main problem here is my model are based on N over O versus O over H. That's why N2 over O2 is telling me something with O above over H. But the relation of N2 over N over O, versus over H is fixed in my model. It's not that fixed in the reality. We don't really know. There is a big scatter in the N over O versus O over H relationship. So that's an apparent good solution, and it's only because my grid of model is not taking into account variation on the N over O versus over H relationships that exist in the reality. So it's not that easy. And the same for S2 over O2. Okay, S over O. Yeah, okay. S over O is less sensitive, and it may be considered as constant. Not that, because O is depleted, S not that much. Okay. The point here is that it's almost vertical, so you cannot determine things, except the very, very high metallicity and so cooled region. But all the guys that we are interested in, perhaps, are those guys. So there is no here good relation to determine abundances. And O2 plus O3 is also a good guy, but look, it's not that good because you first need to know in which part of the diagram you are, and it works fine only with very metal rich or very metal poor region. In the close to solar guys, well, it's also degenerated, so it doesn't. Okay. And I also have the possibility to cut my model, so use matter bounded model from the grid. So I cut at the model at half their size. Okay, so this is a normal, the previously shown grid of model, and this is the one with cut model, so matter bounded model. There seems to be the same, but look, here is the yellow guy, and it was there before. So it's moving in the BPT diagram, all the models. So it adds noise to the results. So this is an illustration of the N2 and O2 over O3 over N2 diagnostics. And this is what is obtained with matter bounded. So you can see that things are moving. So it adds noise to the determination. So as a matter of conclusion, I think physical parameters can be determined in spatially resolved observation in each pixel. It's fine. Okay. Ionic abundances can also be determined. Okay, that's the same. Elemental abundances may be obtained using the previously determined the direct method, okay, using ICF, but take care of this ICF. I show you in two examples that it's rather flat in the example of chlorine over oxygen. It may not be always the case, but okay, it's not that stupid because it's based on similarity of ionization, and it makes sense. Abundances cannot be determined using strong line calibration at all. Okay, it not even think that it may be. No, it doesn't at all. Okay, these methods are statistical first, so determining one single region metallicity from a strong line calibration, it's first a problem because it's statistical method. It can indicate you some gradients from one region to the other one in a given galaxy. Okay, comparing things, but absolute value are not that good. Okay, but for the spaxels, forget it. It cannot be done because it's based on a relation between ionization and metallicity and global ionization. Okay. Ionization source may be determined. I mean, OB shocks, OB stars, shocks, etc., based on the BPT, but with caution. My models have a fixed N over O relation, so even the classical BPT may be shifted a little bit with N over O, but it seems that the upper limit envelope is conserved. That's good news. Okay, and take care that in my model, I have only one relation between N over O, a relationship between N over O and log U versus over H. But there are scatter, so a grid of model should include scatter in this relation. And matter bounded region also add noise. Okay, thanks a lot.